The Soviets landed on Venus. Sort of, and what they found should have rewritten the textbooks. We all have this idea of hellish landscapes and crushing pressure. That's not wrong exactly. But the images sent back, they're not what you think. We've been told a story of monochrome desolation. Consider this. What if some of the data was obscured? What if the Soviets found something they weren't expecting? Something that challenges everything we thought we knew about Venusian geology. Let's examine what the Soviets really found. 90 Earth atmospheres. That's the crushing pressure on Venus. Imagine diving nearly a kilometer beneath the ocean. That's the kind of force we're talking about. And yet, despite this, the Soviets managed to get probes down there. Several of them, actually. Venus. We picture a uniformly orange, hellish landscape, a world perpetually shrouded in thick clouds of sulfuric acid, and the images we've generally seen reinforce that idea. But there's a problem. Those images, they've been processed, massaged, sometimes even outright fabricated from limited data. The Soviets, in their race to beat the Americans in the space race, weren't always completely forthcoming with the raw data, especially if that data didn't fit the prevailing narrative. The Venera program, a series of probes designed to explore our sister planet, achieved the impossible, surviving the extreme temperatures and pressures long enough to send back data and, crucially, images. Venera 9 and 10 were the first to return black and white panoramas from the surface. These showed relatively flat, rocky plains, angular, weathered rocks scattered across the landscape. Nothing particularly surprising given what scientists expected. But here's a question. What if those images were incomplete? Consider the technical limitations of the time. Transmitting data from the surface of Venus through that thick atmosphere was no easy feat. Bandwidth was limited. Data transfer rates were glacial. Image resolution suffered. So the Soviets prioritized certain data points: geological composition, atmospheric pressure, temperature readings. The images, while groundbreaking, were secondary. And then came Venera 13. This probe, landing in 1982, gave us the first color images of the Venusian surface. Suddenly, the orange monochrome world gained a little more nuance. We saw patches of brown, grey, and even hints of orange in the rocks. The landscape looked a bit more complex, a little less uniform. But even these images are not without their questions. The color balance, for example, has been debated for years. Some scientists argue that the original images were significantly altered to emphasize the orange hues. Others claim that the atmospheric conditions on Venus would naturally filter the light, creating a predominantly orange cast. The truth likely lies somewhere in between. But it raises a crucial point. How much of what we know about Venus is based on actual data and how much is based on interpretation and artistic license? What if there are subtle color variations, mineral deposits, or geological features that were simply missed or deliberately suppressed in the original Soviet transmissions? What if the hellish image of Venus, so deeply ingrained in our collective consciousness, is a simplification? Here's what's wild. The Soviets themselves hinted at anomalies. In some of their scientific papers, they alluded to unusual spectral signatures, unexplained reflections, variations in the rock composition that didn't quite fit their established models. These were often dismissed as instrument errors or atmospheric interference. But what if they were something more? The Venera landers were only equipped with basic instruments. They could analyze the composition of the rocks they touched, measure the temperature and pressure, but they couldn't perform detailed mineralogical surveys or analyze the landscape from a distance. They were essentially blindfolded, feeling around in the dark. And the landing sites themselves were chosen based on limited data. The Soviets aimed for relatively flat, safe areas to minimize the risk of damage to the probes. But these areas might not be representative of the entire Venusian surface. What if there are regions with dramatically different geology, hidden beneath the clouds? Regions with evidence of past volcanic activity, hydrothermal vents, or even, dare we say it, evidence of past water. The short lifespan of the Venera landers further limited their ability to explore. They survived for, at most, a couple of hours in the extreme conditions. This meant they could only transmit a limited amount of data before succumbing to the heat and pressure. They were essentially taking snapshots of a single moment in time. Further examination revealed that the Soviets were extremely good at engineering, that's for certain, but the probes were not designed for prolonged exploration. They were designed to survive long enough to prove a point that perhaps they wanted to control the narrative around: the surface of Venus, a surface that to this day remains largely unexplored. The implications extend beyond just our understanding of Venus. It challenges our assumptions about planetary habitability, about the potential for life to exist in extreme environments. If Venus, with its scorching temperatures and crushing pressure, could harbour surprises, what other secrets are hidden on other planets and moons in our solar system? And then there's the question of what happened to the data. Much of the original Soviet data from the Venera missions remains locked away in archives. Some of it has been digitized and made available to researchers, but much of it is still inaccessible. And even the data that is available is often difficult to interpret due to the limitations of the technology and the language barriers. So we're left with a tantalizing glimpse of a world that is far more complex and mysterious than we ever imagined. A world that may hold the key to unlocking some of the biggest secrets of the solar system. How did the Soviets manage to pull this off? Sending probes to another planet, especially one as hostile as Venus, was no small feat. It wasn't just luck. It was a systematic, relentless and sometimes reckless push to explore the unknown. This push manifested in the Venera program, a series of missions designed to pierce the Venusian veil. The program, initiated in 1961, encountered numerous setbacks early on. The initial probes either burned up in the atmosphere, were crushed by the pressure, or simply failed to communicate. But the Soviets, undeterred, learned from each failure. They meticulously analyzed the wreckage, redesigned their probes, and launched again. Each attempt brought them closer to their goal. Consider the engineering challenges. They weren't just dealing with heat, they were dealing with intense pressure, corrosive atmospheric gases, and the constant threat of equipment failure. The probes had to be built like miniature submarines, capable of withstanding immense forces. They needed sophisticated heat shields to protect the delicate instruments inside, and they needed robust communication systems to transmit data back to Earth across millions of miles of space. The Venera probes weren't just thrown together. They were meticulously crafted pieces of engineering designed to survive conditions that would instantly destroy any unprotected object. They were made of titanium alloys, high-temperature ceramics, and other advanced materials. Their electronics were shielded against radiation and extreme temperatures, and their descent modules were designed to slow them down as they plunged through the Venusian atmosphere. One of the key innovations was the use of parachutes. These weren't your typical nylon parachutes. They were made of heat-resistant fabrics and designed to deploy in the dense, turbulent atmosphere of Venus. The parachutes slowed the probes down enough to allow them to survive the initial descent. But even with parachutes, the landing was still incredibly rough. Another crucial element was the design of the landers themselves. They were spherical to evenly distribute the pressure. They were heavily insulated to protect against the extreme heat. And they were equipped with a variety of instruments, including thermometers, barometers, photometers, and even cameras. These instruments were designed to measure the temperature, pressure, and composition of the Venusian atmosphere and surface. The cameras, in particular, were a triumph of engineering. They had to be able to see through the thick clouds and capture images in the dim light of the Venusian surface. They were equipped with special filters to block out the harsh glare, and they were designed to operate in the extreme temperatures and pressures of Venus. The Soviets also developed innovative techniques for transmitting data back to Earth. They used high-powered transmitters and sophisticated antennas to send signals across millions of miles of space. They also developed data compression algorithms to squeeze as much information as possible into each transmission. The Venera program wasn't just about engineering. It was also about scientific discovery. The probes sent back a wealth of data about Venus, including the first-ever images of its surface. These images revealed a barren, rocky landscape, dominated by volcanoes, lava flows, and impact craters. The probes also measured the temperature and pressure of the Venusian atmosphere. They found that the surface temperature was a scorching 900 degrees Fahrenheit, hot enough to melt lead, and the pressure was 90 times that of Earth, equivalent to being a kilometer deep in the ocean. The Venera probes also analyzed the composition of the Venusian atmosphere. They found that it was mostly carbon dioxide with small amounts of nitrogen, sulfur dioxide, and other gases. They also detected traces of water vapor, suggesting that Venus may have once had oceans. The data revealed that Venus was a very different world from Earth. It was a hellish landscape with extreme temperatures, crushing pressures, and a toxic atmosphere. But it was also a world of geological wonders, with towering volcanoes, vast lava plains, and evidence of a dynamic past. The Venera program was a testament to the ingenuity and determination of the Soviet scientists and engineers. Despite the many challenges, they succeeded in exploring one of the most hostile environments in the solar system. They sent back a treasure trove of data that has revolutionized our understanding of Venus. But the story doesn't end there. The Venera data also raised many new questions. What caused Venus to become so different from Earth? Did Venus ever have oceans? And could Venus ever be terraformed into a more habitable planet? These are questions that scientists are still trying to answer today. The Soviets had provided the first glimpse, but it would take decades to fully understand it. I still remember the first time I saw the temperature and pressure readings from the Venera probes. It was almost unbelievable. 900 degrees Fahrenheit, 90 times Earth's atmospheric pressure. It's hard to even wrap your head around those numbers. Let's examine what that actually means for a moment. Imagine standing on the surface of Venus. First, the heat. At 900 degrees Fahrenheit, we're talking about temperatures hot enough to melt lead, tin, and zinc. Any spacecraft landing there needs serious heat shielding to survive for even a short time. Forget about electronics. Most components would simply fail in those conditions. And then there's the pressure. 90 times the pressure at sea level on Earth. That's like being almost a kilometer deep in the ocean. The force is immense, crushing. Any unprotected human would be instantly flattened. The Venera probes themselves were built like thick-walled titanium spheres, specifically to withstand this incredible pressure. But even with that, they were only designed to last a short time. The Soviets understood this, of course. They knew they were sending their probes into an incredibly hostile environment. But they also knew that the potential scientific rewards were worth the risk. The engineering challenges were enormous. The probes had to be designed to withstand not only the extreme heat and pressure, but also the corrosive atmosphere of Venus. They needed to be automated, capable of carrying out their mission without any human intervention. And they needed to be able to transmit their data back to Earth across millions of miles of space. Scientists discovered that the Venusian atmosphere is primarily carbon dioxide. Over 96% of it, actually. On Earth, carbon dioxide is a relatively minor component of our atmosphere, making up only about 0.04%. But on Venus, it's the dominant gas. This massive amount of carbon dioxide is responsible for the planet's intense greenhouse effect, trapping heat and driving surface temperatures to those incredible levels. Mixed in with the carbon dioxide are smaller amounts of nitrogen, sulfur dioxide, and other gases. Sulfur dioxide is particularly interesting because it's a strong indicator of volcanic activity. The Venera probes detected significant amounts of sulfur dioxide in the Venusian atmosphere, suggesting that Venus is still volcanically active today. This supports other evidence that Venus is a geologically dynamic planet, with ongoing volcanic eruptions and lava flows shaping its surface. Measurements showed that there were also traces of water vapor in the atmosphere. Now, this might seem surprising given how incredibly hot and dry Venus is today. But it suggests something really important, that Venus may have once had a lot more water. It's possible that Venus once had oceans, just like Earth. But over billions of years, those oceans evaporated due to the increasing heat from the sun. The water vapor then escaped into space, leaving Venus with its current, bone-dry atmosphere. Think about that for a minute. A planet that may have once been Earth-like with oceans and a potentially habitable environment, transformed into the scorching, hellish world we see today. What happened? How did Venus go so wrong? It's a cautionary tale, a reminder of how delicate and fragile planetary habitability can be. These questions are still actively being researched. The Venera data provided the first clues, but it's going to take more advanced missions and sophisticated modeling to really understand what happened to Venus. The European Space Agency's Venus Express mission and the Japanese Akatsuki orbiter have added to our knowledge, but there's still a lot we don't know. Here's what's wild. The Soviets weren't just aiming to survive, they wanted to take pictures. Imagine the difficulty. You're dealing with extreme heat, crushing pressure, a corrosive atmosphere, and a thick cloud cover that blocks out most of the sunlight. And yet, they managed to capture the first-ever images of the Venusian surface. These images showed a dark, rocky landscape. The analysis continued. Dominating the surface were volcanoes, lava flows, and impact craters. The surface was also surprisingly smooth, suggesting that it had been resurfaced by volcanic activity relatively recently. And then, December 15th, 1970. Somewhere in the Soviet Union, a team of engineers and scientists huddled around monitors, waiting. Venera 7 was plunging into the Venusian atmosphere. This wasn't just another space probe, it was a do-or-die moment for the Soviet space program. Their previous attempts to land on Venus had all failed, ending in communication loss or outright destruction of the probes. This time they were determined to succeed, or at least get something back. Anything. The probe endured atmospheric entry, deploying its parachute as planned. But as it descended through the dense, superheated air, disaster struck. The parachute partially tore, sending Venera 7 plummeting towards the surface. Imagine the tension in that control room. Years of work, millions of rubles, all hanging on a fragile spacecraft, hurtling toward an alien world. Then, silence. For what felt like an eternity, there was no signal. Had Venera 7 been crushed on impact? Had the intense heat fried its electronics? Was this another failure to add to the growing list? But then, a miracle. After what seemed like an age, a faint signal crackled through the speakers. It was weak, barely audible, and lasted for only 23 minutes. But it was there. Venera 7 had survived the landing and was transmitting data from the surface of Venus. Those 23 minutes were some of the most valuable in the history of space exploration. They provided the first direct measurements of the temperature of the Venusian surface, a scorching 475 degrees Celsius, 887 degrees Fahrenheit. This confirmed what scientists had suspected, but now they had undeniable proof. Venus was hellishly hot. The signal also gave a pressure reading, 90 atmospheres. That's 90 times the pressure on Earth's surface, equivalent to being almost a kilometre deep in the ocean. It's hard to even fathom those conditions. Think about the engineering challenges. Designing a probe that could withstand that kind of heat and pressure, not to mention the corrosive atmosphere, was an incredible feat. The Soviets had to develop new materials and technologies just to make it possible. Venera 7 wasn't designed to take pictures. Its primary mission was to measure temperature and pressure. But the fact that it survived at all and managed to transmit data was a monumental achievement. It proved that it was possible to land on Venus and get information back, paving the way for future missions. The data revealed that the surface was relatively flat and rocky. Further, the probe detected very little wind at the surface, which was surprising, considering the dense atmosphere. Scientists had expected stronger winds, but the measurements showed that the air was relatively calm near the ground. The success of Venera 7 was a major propaganda victory for the Soviet Union. It demonstrated their technological prowess and their commitment to space exploration, even in the face of daunting challenges. The mission captured the world's imagination and inspired a new generation of scientists and engineers. But beyond the political and technological achievements, Venera 7 provided invaluable scientific data that changed our understanding of Venus forever. It confirmed the extreme conditions on the surface and gave us our first glimpse of what it was really like on that alien world. What's interesting is how little the data changed the next mission's parameters. Venera 8 launched almost 2 years later, in March 1972, and reached Venus that July. It was designed with a similar goal, to land and transmit data about the surface. But Venera 8 had an additional instrument, a photometer to measure the amount of light reaching the surface. Remember that thick cloud cover? The Soviets wanted to know just how much sunlight penetrated it. Venera 8 survived for 50 minutes after landing, transmitting valuable data about the atmosphere and surface. The photometer measurements revealed that the surface was surprisingly well lit despite the clouds. It was like a very cloudy day on Earth, but still bright enough to see. This was good news for future missions that would attempt to take pictures. The probe also carried a gamma-ray spectrometer which measured the radioactive elements in the surface rocks. The data showed that the rocks were similar in composition to terrestrial granite, suggesting that Venus had a differentiated crust like Earth. The analysis continued, and the Soviets were racking up more and more firsts in the exploration of Venus. They were pushing the boundaries of what was possible, and in doing so, they were unlocking the secrets of a planet that had long been shrouded in mystery. And then came Venera 9. We expected blurry, indistinct images. What we got were glimpses of an alien world, stark and surprisingly detailed. The Venera 9 and 10 missions, both launched in 1975, represented another leap forward. These weren't just landers designed to survive for a few minutes. They were equipped with panoramic telephotometers, essentially cameras, designed to send back the first-ever images from the surface of Venus. The challenges were immense. The extreme temperature and pressure were constant threats to the probe's delicate electronics. The thick atmosphere scattered light, making it difficult to obtain clear images. And of course, there was the ever-present risk of simply failing during the long journey through space or upon landing. Venera 9 touched down on Venus on October 22, 1975, and Venera 10 followed 3 days later. Both probes landed during daylight, which was crucial for capturing images. But the light wasn't like daylight on Earth. It was a dim, diffused glow filtered through the dense clouds. The cameras on Venera 9 and 10 were unlike anything we'd used before. They used a mechanical scanning system to create panoramic images. A mirror rotated slowly, reflecting light onto a photosensitive element. As the mirror turned, it built up a strip of data, line by line, to produce a partial image. The process was slow and painstaking, but it was the only way to get a picture in those conditions. The images that Venera 9 sent back were astounding. They revealed a landscape of sharp, angular rocks scattered across a relatively flat surface. The rocks looked weathered and eroded, suggesting that they had been exposed to the harsh Venusian environment for a long time. The horizon was visible, but it was hazy and indistinct, obscured by the dense atmosphere. The images were black and white, but scientists were able to infer the approximate color of the surface based on spectral data. It appeared that the rocks had a reddish-orange hue, likely due to the presence of iron oxides. It's like looking at a rusted landscape, but instead of being cold, it's hot enough to melt lead. Venera 10's images showed a similar landscape, but with some subtle differences. The rocks were more rounded and smoother, suggesting that they had been shaped by different geological processes. There were also indications of layering in some of the rocks, hinting at a complex history of volcanic activity and erosion. It's important to remember that these weren't high-resolution photographs like we're used to seeing from Mars rovers. The images were grainy and distorted, but they were still revolutionary. They provided the first direct evidence of what the surface of Venus actually looked like. These first images revealed that the surface of Venus was surprisingly rocky. Before these missions, some scientists thought the surface might be covered in dust or even liquid. The Venera images put those theories to rest. The panoramic images also provided valuable information about the geological processes that had shaped the surface of Venus. The angular rocks suggested that there had been relatively recent volcanic activity, while the smoother rocks hinted at the effects of erosion and weathering. The images from Venera 9 and 10 weren't just pretty pictures, they were scientific data. By studying the images, scientists could learn about the composition of the rocks, the topography of the surface, and the processes that had shaped the planet over billions of years. The data revealed that the surface of Venus was much more varied and complex than previously thought. It wasn't just a flat, featureless plain, it was a dynamic landscape with mountains, valleys, and volcanoes. The Venera 9 and 10 missions were a triumph of engineering and scientific ingenuity. They demonstrated that it was possible to explore even the most hostile environments in our solar system, and they opened up a new window onto the mysteries of Venus. Consider what it took to build and launch these probes, send them across millions of miles of space, and land them safely on a planet where the temperature is hot enough to melt lead. The challenges were immense, but the rewards were even greater. The success of Venera 9 and 10 paved the way for future missions to Venus, including the Venera 11, 12, 13, and 14 landers, which sent back even more detailed images and data. Each mission built upon the successes of the previous ones, gradually unraveling the secrets of this enigmatic planet. The implications extend far beyond just understanding Venus. By studying Venus, we can learn about the processes that shape all planets, including our own. we can gain insights into the evolution of planetary atmospheres, the dynamics of volcanic activity, and the potential for life beyond Earth. The Venera missions also taught us valuable lessons about the challenges of exploring extreme environments. The lessons learned from these missions have been applied to other space exploration efforts, including the exploration of Mars, the outer planets, and even the moons of Jupiter and Saturn. The legacy of Venera 9 and 10 lives on today, inspiring a new generation of scientists and engineers to push the boundaries of space exploration. These missions were a testament to human curiosity, ingenuity, and determination. Here's what's wild. Even with the limited technology of the 1970s, the Soviets managed to capture images that still captivate us today. They showed us that even in the most hostile environments, there is beauty and wonder to be found. And then came the color images. There's a real problem with the initial color data from the Venera landers. It's not wrong exactly, but it's incomplete. Understanding the challenges they faced helps put those images in context. Getting accurate color information from the surface of Venus is an immense challenge. The thick atmosphere scatters light, filtering out certain wavelengths and creating a pervasive orange hue. Plus, the intense heat and pressure wreak havoc on electronic components, making accurate color calibration difficult. The Venera 11 and 12 missions, launched in 1978, continued the exploration of Venus, but unfortunately they didn't produce any usable images. Both landers failed relatively quickly after landing due to the extreme heat and pressure. Venera 11 lasted only 95 minutes, and Venera 12 survived for 110 minutes. This was still enough time to gather atmospheric data, which proved invaluable, but the cameras remained silent. It wasn't until Venera 13 and 14 in 1982 that the Soviets finally succeeded in capturing color images of the Venusian surface. These missions were a major step forward, equipped with advanced color cameras and drills to collect soil samples for analysis. Venera 13 landed in the Lavinia Planitia region, while Venera 14 touched down about 950 kilometers away near the eastern flank of Phoebe Regio. Both sites were relatively flat, rocky plains. The images from Venera 13 were particularly striking, revealing a landscape dominated by reddish-brown rocks and soil. Patches of darker material were also visible, possibly indicating variations in mineral composition. The sky, as expected, appeared a hazy orange color due to the atmospheric filtering. But here's the thing. The colors we see in those images aren't exactly what a human eye would perceive. The cameras used color filters to separate the light into different wavelengths. These filters allowed scientists to reconstruct color images, but the process wasn't perfect. The intense heat and pressure, combined with the limited lifespan of the landers, meant that the color calibration was somewhat imprecise. The Venera 14 images showed a similar landscape, but with some subtle differences. The rocks appeared slightly darker and more grey in tone, suggesting variations in the local geology. One of the most notable features in the Venera 14 images was a lens cap that had ejected from the probe and landed in the field of view of one of the cameras. This accidental inclusion provided a useful reference point for calibrating the color and distortion in the images. It's a bit ironic that a discarded piece of equipment ended up being a valuable scientific tool. The soil samples collected by Venera 13 and 14 provided further insights into the composition of the Venusian surface. The samples were analyzed using X-ray fluorescence spectrometers, which revealed the presence of elements like iron, potassium, magnesium, and aluminum. The data suggested that the rocks were primarily composed of basalt, a common volcanic rock found on Earth and other planets. The analysis also revealed that the Venusian soil was surprisingly rich in potassium, which was unexpected. This finding raised questions about the processes that had shaped the planet's surface and the role of volcanism in its evolution. Was there something unique about Venusian volcanism that concentrated potassium in the soil? Or were other geological processes at play? The Venera missions also carried instruments to measure the density and composition of the Venusian atmosphere. The data revealed that the atmosphere is composed primarily of carbon dioxide, with small amounts of nitrogen, argon, and other gases. The density of the atmosphere is about 90 times that of Earth's, creating the crushing pressure on the surface. The measurements also confirmed the presence of sulfuric acid clouds in the upper atmosphere, which contribute to the planet's high reflectivity and its yellowish appearance from space. These clouds are formed by the interaction of sulfur dioxide and water vapor, and they play a key role in the planet's greenhouse effect. The combined data from Venera 11 through 14 painted a picture of Venus as a hellish world, with a scorching surface, a toxic atmosphere, and a landscape shaped by intense volcanic activity. Yet, even in this extreme environment, there was evidence of geological complexity and a history that was still being unraveled. Scientists discovered some of the basaltic rocks were surprisingly young, geologically speaking, indicating that volcanism was still active on Venus. This was a major discovery as it suggested that Venus was not a dead planet, but a dynamic and evolving world. The implications extend to understanding the planet's internal heat and its potential for geological activity in the future. So, when you look at those color images from Venera 13 and 14, remember that they're not just pretty pictures. They're the result of a monumental effort to explore one of the most hostile environments in our solar system. They're a testament to human ingenuity and our insatiable curiosity about the universe, and they represent just one piece of the puzzle in our ongoing quest to understand Venus. Consider this: the Soviets managed to get color images back to Earth despite all those challenges. It's incredible, really. The analysis continued. Something pretty weird turned up in the images. I'm talking about what some scientists have called the disks, scattered across the Venusian landscape in some of the Venera panoramas, with these strange, flat, disk-like objects. What were they? That's the question that had planetary scientists scratching their heads for years. At first glance, they almost looked like some kind of manufactured object, like someone dropped a hubcap on Venus, but of course, that's incredibly unlikely. The Soviets hadn't littered the planet, and no one else had made it there yet. So, what natural processes could create such regular shapes? One of the earliest and most obvious suggestions was that they were some kind of rock formation. Venus is a volcanic world. It's covered in basaltic plains, so it's not unreasonable to assume that these disks were just unusual volcanic rocks. Maybe they were formed from lava flows that cooled in a particular way. Perhaps some kind of layering or differential erosion created these shapes over eons. One possibility is that they were concretions, mineral formations that grow within sedimentary rocks. On Earth, concretions can take on all sorts of weird and wonderful shapes, including disc-like forms. However, there's a problem with this explanation. Venus doesn't really have sedimentary rocks in the way we think of them on Earth. The intense heat and pressure on the surface tend to obliterate any sedimentary structures. Another suggestion was that the disks were related to the lander itself. Could they be debris that fell off during landing? Or perhaps they were part of the landing platform, somehow distorted by the extreme conditions. Again, there are problems. The disks appear in multiple images from different Venera landers. They're also located at varying distances from the spacecraft. It seems unlikely that debris from the lander could have spread so widely and consistently. There's also the shape to consider. These disks are remarkably flat and circular. It's hard to imagine how a random piece of debris could end up with such a regular form. Perhaps the most intriguing hypothesis involves atmospheric phenomena. Venus has an incredibly dense and turbulent atmosphere. It's possible that some kind of atmospheric process could have sculpted the surface into these shapes. Consider the wind. Venusian winds are incredibly strong at certain altitudes, even if they're relatively calm at the surface. Could these winds have eroded the rocks into disk shapes over millions of years? Or maybe there's some kind of electrostatic effect at play. Venus's atmosphere is known to be highly electrically charged. Could this electrical activity have caused dust particles to clump together and form these disk-like structures? It's certainly a more speculative idea, but it's not entirely out of the question. We know that electrical forces can play a significant role in shaping planetary surfaces. Just look at the dust devils on Mars, which are thought to be driven by electrostatic charges. The difficulty is that we simply don't have enough data to say for sure. The Venera landers only provided a few limited snapshots of the Venusian surface. They weren't equipped to carry out detailed geological surveys or atmospheric measurements. To really understand the origin of the disks, we need more data. We need to send new missions to Venus equipped with advanced instruments that can analyze the composition and structure of these features. We need to study the Venusian atmosphere in greater detail to understand the role of wind and electrical activity in shaping the surface, and ideally, we need to collect samples of these disks and bring them back to Earth for laboratory analysis. In the meantime, the disks remain an enigma. They're a reminder of how much we still don't know about Venus, despite the pioneering efforts of the Venera missions. They're also a testament to the power of scientific curiosity, which drives us to explore even the most hostile and mysterious corners of our solar system. It's possible they are just rocks. But they could be something far more exotic. The truth is, without further exploration, we may never know for sure. And then there's the question of color. If even a fraction of these mysteries prove out, the implications extend to the biggest question of all. Could there be life on Venus? It sounds absurd, I know. Venus is our solar system's hellish twin, a pressure cooker with a toxic atmosphere and surface temperatures hot enough to melt lead. But the more we learn about Venus, the more hints we find that it might not always have been this way. Consider the evidence suggesting that Venus once had liquid water on its surface. Computer models of Venus's early climate indicate that it could have been much cooler and wetter than it is today. It's even possible that Venus had oceans for billions of years. If Venus did have oceans, it could have been habitable. Liquid water is essential for life as we know it, and a stable, temperate climate could have allowed life to evolve. Now, I'm not saying that we've found definitive proof of past life on Venus, but there are some intriguing clues that are worth exploring. One of the most intriguing is the detection of phosphine in the Venusian atmosphere. In 2020, a team of astronomers announced that they had detected phosphine gas in the clouds of Venus. Phosphine is a colorless, flammable gas that is usually produced by biological activity. On Earth, it's found in swamps, marshes, and the guts of animals. It can also be produced industrially, but there are no known industrial sources on Venus. The discovery of phosphine on Venus sparked a flurry of excitement and debate. Some scientists argued that it could be a sign of life, while others suggested that it could be produced by non-biological processes. The problem is that we don't fully understand the chemistry of the Venusian atmosphere. It's possible that there are unknown chemical reactions that could produce phosphine without the need for life. However, no one has yet been able to come up with a convincing, non-biological explanation for the presence of phosphine in the amounts that have been detected. The phosphine detection is still controversial, and further research is needed to confirm its existence and determine its origin. But if it is confirmed to be of biological origin, it would be a game changer. It would mean that life exists, or at least existed, on Venus. And if life exists on Venus, it would have profound implications for our understanding of the universe. It would mean that life is not unique to Earth and that it could be much more common than we thought. The discovery of life on Venus would also raise new questions about the origin and evolution of life. How did life arise on Venus? Did it evolve independently of life on Earth? Or was there some kind of exchange of life between the two planets? These are all questions that we would need to answer if we were to find evidence of life on Venus. Of course, the possibility of life on Venus is still highly speculative. We need more data before we can say anything for sure. But the fact that we're even talking about it is a testament to how much our understanding of Venus has changed in recent years. And it's not just the phosphine detection that has scientists intrigued. There are other hints that Venus might be more habitable than we thought. Consider the so-called anomalous UV absorption in the Venusian atmosphere. For decades, scientists have known that there is something in the Venusian atmosphere that absorbs ultraviolet light. The identity of this UV absorber is unknown, but some scientists have suggested that it could be a pigment produced by microorganisms. These microorganisms could be living in the clouds of Venus, where the temperature and pressure are more moderate than on the surface. The clouds of Venus are made up of sulfuric acid droplets, but they also contain water and other nutrients that could support life. It's a long shot, but it's not impossible. And if there are microorganisms living in the clouds of Venus, they could be responsible for the phosphine detection and the anomalous UV absorption. Again, I want to emphasize that this is all highly speculative. We don't have any direct evidence of life on Venus. But the evidence is intriguing enough to warrant further investigation. The Venera landers weren't equipped to search for life, but future missions could be. A dedicated mission to search for life on Venus would need to carry sophisticated instruments that can analyze the composition of the atmosphere and clouds and look for signs of biological activity. It would also need to be able to withstand the harsh conditions on Venus. The lander would need to be able to survive the intense heat and pressure and the corrosive effects of the sulfuric acid clouds. It's a challenging task, but it's not impossible, and the potential rewards are enormous. If we were to find evidence of life on Venus, it would be one of the most important scientific discoveries of all time. And there's one more piece to this puzzle: the color of the surface. You've probably seen the images, those orange-tinted, grainy photos from the surface of Venus. But what about the view from the clouds? In 1985, the Soviets, in collaboration with several international partners, launched the Vega program. These missions weren't just about landing, they also deployed something truly unique: balloons. 2 balloons, to be exact. These weren't your average party balloons, mind you. These were sophisticated, helium-filled probes designed to float through the densest, most active layer of the Venusian atmosphere, about 53 kilometers above the surface. Think about that for a second. 53 kilometers. That's where the temperature and pressure are surprisingly Earth-like. It's also where those mysterious UV absorbers hang out, potentially indicating microbial life. The Vega balloons were designed to drift with the winds, acting like free-floating weather stations in the Venusian clouds. Each balloon was equipped with instruments to measure temperature, pressure, cloud density, and even the presence of aerosols. Now, deploying a balloon in the clouds of Venus is no easy feat. The balloons had to be incredibly robust to withstand the corrosive sulfuric acid environment. They were constructed from a Teflon-like material and pressurized to maintain their shape. Each balloon was only about 3.5 meters in diameter, and they were released from the Vega landers as they descended through the atmosphere. Once deployed, the balloons inflated and began their journey, transmitting data back to Earth via the landers. And what a journey it was! The balloons floated for roughly 46 hours each, covering a staggering distance of about 11,600 kilometers. That's almost a third of the way around the planet. The constant winds at that altitude whip around Venus at incredible speeds, much faster than the planet itself rotates. This phenomenon, known as superrotation, is still not fully understood. The Vega balloons provided valuable data to help scientists unravel this mystery. The data revealed a dynamic and complex cloud structure. The balloons detected significant temperature variations and turbulence, indicating active weather patterns in the Venusian atmosphere. They also confirmed the presence of 3 distinct cloud layers, each with different densities and compositions. One of the most intriguing findings was the detection of bursts of lightning. The Venera missions had already hinted at lightning activity, but the Vega balloons provided more direct evidence. Lightning on Venus is thought to be generated by the movement of ice crystals in the upper atmosphere, much like on Earth. However, the exact mechanisms are still debated. But let's get back to those sulfuric acid clouds. It sounds like the stuff of nightmares, doesn't it? But the Vega balloons showed that the cloud particles weren't just sulfuric acid. They also contained other elements, including chlorine and phosphorus. Phosphorus. That's the same element that's at the heart of the phosphine controversy. The detection of phosphorus in the cloud particles by the Vega balloons doesn't necessarily confirm the presence of phosphine gas, but it does suggest that phosphorus compounds are present in the Venusian atmosphere. And that's yet another piece of the puzzle. The Vega balloons also provided valuable information about the vertical structure of the Venusian atmosphere. They showed that the temperature and pressure gradients were much steeper than previously thought. This information is crucial for understanding the planet's overall energy balance and climate. The balloons weren't just about atmospheric science, though. They also carried instruments to search for evidence of volcanic activity. Venus is known to be volcanically active, and some scientists believe that volcanic eruptions may play a significant role in shaping the planet's atmosphere. The Vega balloons didn't directly detect any active volcanoes, but they did measure fluctuations in sulfur dioxide levels, which could be indicative of volcanic outgassing. Further research is needed to confirm this connection, but the Vega data provides valuable clues. Here's what's wild. The Vega program remains the only instance of crewless balloons being deployed in another planet's atmosphere. That's right. For all our advances in space exploration, we haven't sent another balloon to float through another planet's skies since 1985. Why not? Well, there are a few reasons. Balloon missions are complex and challenging. They require careful planning and execution, and they're not without risk. There's always the possibility that the balloon could fail or that the instruments could malfunction. Also, landing missions tend to get more of the spotlight. A lander on the surface can collect samples, take high-resolution images, and conduct a wide range of experiments. Balloons, on the other hand, are limited to atmospheric measurements. But the Vega balloons demonstrated the unique value of this type of exploration. They provided a global perspective on the Venusian atmosphere that couldn't have been obtained from a lander alone. They also showed that it's possible to survive and operate in the harsh conditions of Venus for extended periods. The Vega balloons may have been a one-off, but they left a lasting legacy. They showed us that Venus is a far more dynamic and interesting planet than we ever imagined, and they paved the way for future balloon missions which could one day search for life in the clouds of Venus. The analysis continued. The Soviets' Venus data faced an uphill battle for acceptance in the West. It wasn't just about scientific findings. Cold War tensions cast a long shadow over everything. Consider the environment. For decades, Western scientists had built up a model of Venus in their minds, based on limited data. Flyby missions like those from the Mariner and Pioneer programs provided snapshots, but they didn't offer the sustained in-situ measurements that the Soviet probes delivered. There was a reluctance to overturn established ideas even when presented with compelling evidence. It's human nature, really. And then there was the language barrier. Much of the initial Soviet analysis was published in Russian, making it inaccessible to many Western scientists. Translation takes time and nuances can be lost. By the time English versions became available, the initial impact was often diminished. But more than that, there was a certain degree of skepticism rooted in the political climate. The Cold War fostered an environment of distrust. Any data coming from the Soviet Union was often viewed with suspicion, even if it was purely scientific. There was a concern that the data might be biased, incomplete, or even falsified for propaganda purposes. It's important to remember that this wasn't just about Venus. The space race was a key battleground in the Cold War, and both sides were vying for technological and scientific supremacy. Each achievement was seen as a victory, and each setback as a defeat. In that context, accepting Soviet findings outright could be seen as conceding ground. Let's examine some specific examples. The high surface temperatures reported by Venera landers were initially met with disbelief. Western scientists questioned the accuracy of the instruments, suggesting that they might be affected by the extreme heat. It took independent confirmation from American missions to fully validate the Soviet measurements. Similarly, the Soviet data on the composition of the Venusian atmosphere was sometimes challenged. The high abundance of sulfur dioxide, for instance, was initially attributed to local variations or instrumental errors. It wasn't until later that the global significance of sulfur dioxide as a major component of the atmosphere was recognized. The dust storm findings from Venera 11 and Venera 12 also faced resistance. Some Western scientists argued that the observed particles might be localized dust devils or other transient phenomena. The idea of a planet-wide dust storm seemed too extreme, too different from anything observed on Earth. Even the Vega balloon results weren't immune to skepticism. Some questioned the accuracy of the instruments, particularly the sulfur dioxide measurements. Others suggested that the observed fluctuations might be due to atmospheric turbulence rather than volcanic activity. It wasn't all political, of course. There were genuine scientific disagreements and uncertainties. Venus is a complex planet, and interpreting the data is never straightforward. Different research groups can arrive at different conclusions, even when working with the same data. However, the Cold War undoubtedly amplified the skepticism surrounding the Soviet Venus program. It created a climate of distrust that made it harder for Soviet scientists to gain acceptance for their findings. Over time, as more data became available from both Soviet and Western missions, the picture of Venus began to converge. Independent measurements confirmed many of the Soviet findings, and the initial skepticism gradually faded. The importance of the Soviet Venus program became increasingly clear, and its contributions to our understanding of the planet were finally recognized. What is important here is that the Soviet program forced Western scientists to reevaluate their assumptions about Venus. It challenged established ideas and opened up new avenues of research. The Vega balloons, in particular, demonstrated the value of atmospheric exploration and paved the way for future balloon missions to other planets. Now, the legacy of the Soviet Venus program is undeniable. The Venera and Vega missions provided a wealth of data that continues to be analyzed and reanalyzed by scientists around the world. The findings have helped to shape our understanding of Venus as a dynamic and complex planet, with a unique atmosphere and a fascinating geological history. But it's also a cautionary tale about the dangers of political bias in science. The Cold War created an environment in which scientific findings were sometimes viewed through a political lens, hindering the progress of knowledge. It's a reminder that science should be driven by evidence, not by ideology. The story of the Soviet Venus program is a story of scientific discovery, technological innovation, and political intrigue. It's a story of how scientists from different countries, working in the midst of the Cold War, were able to overcome political barriers and contribute to our understanding of one of the most enigmatic planets in our solar system. The implications extend beyond just Venus. 47 missions. That's how many attempts have been made to land on or explore Venus. And while many failed, the sheer persistence speaks volumes about our enduring fascination with Earth's sister planet. The Soviets may have blazed the trail with early surface data, but what does the future of Venus exploration actually look like? Well, several new missions are on the horizon, poised to revolutionize our understanding of this scorching world. Think of it as a new Venus era. NASA, for example, has two ambitious missions in the works, Da Vinci and Veritas. Da Vinci, short for Deep Atmosphere Venus Investigation of Noble Gases. Chemistry and imaging will plunge through the Venusian atmosphere, sampling its composition as it descends. Consider this. It's the first mission designed to study Venus's atmosphere while descending through it. It will measure the abundance of noble gases and other key elements, providing insights into the planet's formation and evolution. Da Vinci will also capture high-resolution images of the surface, potentially revealing clues about Venus's geological history. It's like sending a probe on a skydive through hell, but with scientific instruments instead of a parachute. Well, it has a parachute, just not instead of scientific instruments. Veritas, on the other hand, will map Venus's surface in unprecedented detail using radar. Veritas stands for Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy. This mission will create a global topographic map and search for signs of active volcanism and tectonic activity. Scientists suspect that Venus may still be geologically active, and Veritas will help to confirm or refute this hypothesis. Imagine peeling back the thick clouds to reveal the hidden face of Venus, its mountains, valleys, and lava flows laid bare. The European Space Agency, ESA, is also planning its own Venus mission, Envision. Envision will be an orbiter carrying a suite of instruments to study Venus's atmosphere and surface. It will work in concert with Da Vinci and Veritas to provide a comprehensive picture of the planet. Envision will investigate the planet's geological history, search for evidence of past or present volcanic activity, and study the interaction between the atmosphere and the surface. Think of it as the all-seeing eye, providing a global perspective on Venus's complex system. But it's not just government space agencies that are interested in Venus. Private companies are also starting to explore the possibility of Venus missions. Rocket Lab, for instance, launched a private mission to Venus to probe the clouds for signs of life. Let's examine that for a moment. Life on Venus. It sounds like science fiction, but some scientists believe it's not entirely impossible. The idea is that microbial life could potentially exist in the upper layers of Venus's atmosphere, where conditions are slightly more temperate and there's liquid water in the form of sulfuric acid droplets. The Rocket Lab mission aims to search for organic molecules and other potential biosignatures in these clouds. It's a long shot, but the potential payoff is enormous. Imagine discovering life on another planet in our solar system. What's particularly interesting is how these future missions are building upon the legacy of the Soviet Venus program. Da Vinci, for example, will use some of the same techniques that the Venera probes use to analyze the atmosphere. Veritas will build on the radar mapping data collected by the Magellan mission, which itself was informed by the Soviet experience. Envision will benefit from the atmospheric data gathered by the Vega balloons. It's like a relay race, each mission passing the baton to the next, building on previous discoveries and pushing the boundaries of our knowledge. The implications extend beyond just understanding Venus itself. By studying Venus, we can learn more about the processes that shape planetary evolution. Venus is often considered an analogue to early Earth, so understanding its history can provide insights into our own planet's past and future. It can also help us to assess the habitability of other planets in our solar system and beyond. If we can understand why Venus became so inhospitable, we can better understand what makes a planet habitable in the first place. Here's what's wild. These missions are not just about answering scientific questions. They're also about developing new technologies and capabilities. Da Vinci, for instance, will use a new type of heat shield to protect itself from the extreme temperatures of the Venusian atmosphere. Veritas will use a new type of radar to map the surface with unprecedented precision. Envision will use new types of spectrometers to analyze the composition of the atmosphere and surface. These technologies could have applications in other areas of space exploration, such as missions to Mars or the outer solar system. And then there's the long-term vision of human exploration. While Venus is not currently a prime candidate for human colonization, some scientists and engineers are exploring the possibility of establishing a human presence in the Venusian atmosphere. The idea is to create floating habitats in the upper atmosphere where conditions are more Earth-like. These habitats could be used for scientific research, resource extraction, and even tourism. It's a far-fetched idea, but it highlights the enduring human desire to explore and colonize new worlds. Further examination reveals that the future of Venus exploration is bright. With a new generation of missions on the horizon, we are poised to unlock the secrets of this enigmatic planet. These missions will not only expand our knowledge of Venus, but also advance our understanding of planetary evolution, habitability, and the potential for life beyond Earth. The legacy of the Soviet Venus program lives on, inspiring new generations of scientists and engineers to reach for the stars, or, in this case, the scorching clouds of Venus. What is really going to be fascinating is seeing how these new discoveries change our understanding of our own planet. How much have we underestimated Venus? The Soviets, with their relentless Venus program, gave us a glimpse of a world far more complex and dynamic than we ever imagined. But decades later, are we truly seeing the full picture? It's easy to dismiss Venus as a hellish wasteland, a cautionary tale of a runaway greenhouse effect. And sure, the surface is hot enough to melt lead, the atmosphere is thick with toxic gases, and the pressure is crushing. But the Soviet missions, particularly Venera 13 and 14, hinted at something more. A planet with a history, with geological processes at play, and perhaps even with a past that was far more Earth-like than its present. Those grainy black and white images transmitted from the surface were revolutionary at the time. They showed us a landscape of volcanic rock, evidence of past eruptions, and a surface shaped by intense heat and pressure. But they also raised a host of questions. What was the composition of those rocks? What forces shaped the Venusian terrain? And what secrets were hidden beneath the surface? The Soviets did their best to answer these questions with the technology they had available. They analyzed soil samples, measured atmospheric conditions, and mapped portions of the Venusian surface with radar. But their missions were short-lived, and the data they collected was limited. They scratched the surface, metaphorically and literally, but they didn't have the tools to dig deeper. Now, with a new generation of Venus missions on the horizon, we have the opportunity to revisit these questions with far more advanced technology. Da Vinci will descend through the Venusian atmosphere, analyzing its composition and structure in unprecedented detail. Veritas will map the surface with high-resolution radar, revealing hidden geological features and searching for evidence of past or present volcanic activity. Envision will study the planet's atmosphere and surface composition, providing insights into its evolution and potential for habitability. But it's not just about having better technology, it's also about asking the right questions. For years, Venus was largely ignored by the Western space programs, overshadowed by the focus on Mars. But in recent years, there's been a growing recognition that Venus holds vital clues to understanding planetary evolution and the conditions that make a planet habitable. One of the key questions is why Venus and Earth, which are similar in size and composition, evolved so differently. What triggered the runaway greenhouse effect on Venus? Was there a period in Venus's history when it was more Earth-like, perhaps even with liquid water on its surface? And what lessons can we learn from Venus to help us protect our own planet from a similar fate? Consider the possibility that Venus experienced plate tectonics in its early history, much like Earth. The evidence is still debated, but some scientists believe that certain geological features on Venus, such as tesserae, highly deformed regions of terrain, could be remnants of ancient plate boundaries. If Venus did have plate tectonics, it could have played a crucial role in regulating its climate and creating conditions suitable for life. Furthermore, the role of volcanism on Venus cannot be understated. The planet is covered in volcanic features, including vast lava plains, shield volcanoes, and coronae, unique volcanic structures. Volcanic eruptions could have released massive amounts of greenhouse gases into the atmosphere, contributing to the runaway greenhouse effect. But they could have also played a role in shaping the planet's surface and creating temporary habitats for life. Scientists discovered that lightning strikes are common in the Venusian atmosphere, and they are thought to be associated with volcanic eruptions. These lightning strikes could have generated organic molecules, which are the building blocks of life. It's also worth noting that the upper atmosphere of Venus, at an altitude of about 50 kilometers, has temperatures and pressures similar to those found on Earth. Some scientists have proposed that microbial life could exist in this region, floating in the clouds and feeding on chemical energy. It's a long shot, but it's not entirely impossible. The implications extend far beyond Venus itself. By studying Venus, we can gain a better understanding of the factors that determine planetary habitability and the potential for life beyond Earth. We can also learn valuable lessons about climate change and the importance of protecting our own planet's environment. The Soviet Venus program was a remarkable achievement, but it was just the beginning. With a new generation of missions on the horizon, we are poised to unlock the secrets of this enigmatic planet and rewrite our understanding of planetary evolution. And who knows, maybe we'll even find evidence of life on Venus, past or present. The data is incomplete, and there's still a lot to explore. We must examine the surface features again and rethink the timeline. Maybe it's not as dead as we think. If you're interested in learning more about Venus and the search for life beyond Earth, subscribe for future updates.